Hello, my name is Trung Nguyen, and the co-author of this presentation is Yuanchao Lee, my postdoc. We are from the Department of Chemical and Petroleum Engineering of the University of Kansas. The title of this presentation is A Solid Liquid High Energy Density Storage Concept for Redox Flow Batteries and its demonstration in a hydrogen vanadium system. The presentation is outlined as follows. First, I will provide the background information and the motivation for this work, followed by the solid liquid storage concept and the temperature swing method used to enable this concept in a redox flow battery. Next, I will present some of the key operational requirements for this approach and the discoveries found in this study. Then I will show the results of the demonstration of this concept in a hydrogen vanadium flow battery system. Finally, I will summarize the findings and discuss our future work in this area and end with the acknowledgement of the financial support of this work. Existing data show that electricity from wind is economically competitive with that from carbon-based sources, while that from solar is becoming competitive in some geographical locations and markets. Deployment beyond 20% of these two sustainable but highly variable energy sources is either problematic because the electrical distribution system cannot handle fluctuations of this scale, or economical because the excess capacity during low demand is not utilized and does not bring economic benefits to the owners, unless some economical energy storage solutions are available. To go beyond 50%, wind and solar have to become more reliable sources, because once the fossil fuel sources are reduced to 50% or less, there is no excess baseload capacity from other sources to make up for losses at this scale. Having sufficient energy storage capacity to handle the unpredictable daily variability is not enough. There must be sufficient energy storage capacity to handle the unpredictable long-term availability for wind and solar to become major sources of electricity. In summary, solar and wind can become reliable sources of electricity if the energy storage capacity for these sources approaches that of fossil fuel-based sources, like, for example, 5-day on-site supply of coal. Redox flow batteries consists of a power generation unit that is separated from the external energy storage tanks and offer flexible power and energy designs and are highly suitable for this large-scale energy storage application. Excess electrical energy from wind and solar sources is stored by these redox flow batteries in some aqueous or non-aqueous soluble ions in the electrolyte solution. Because of the low solubility of most ionic materials in aqueous and non-aqueous solvents, typically between 1 to 2 molar, these redox flow batteries have low energy density. For example, the energy density of the all vanadium redox flow battery is about 20 watt-hour per kilogram, while that of the lithium-ion batteries averages about 200 watt-hour per kilogram. So you can see to store a lot of energy requires a very large volume of electrolyte solution, a large number of tanks, and a lot of floor space. The cost of storage tanks and the floor space for these tanks are major issues for the redox flow batteries users. For example, a 4-hour all vanadium redox flow battery system, the electrolyte storage tanks constitute greater than 50% of the total floor space and greater than 10% of the system cost. To meet the 5-day energy storage requirement for long duration energy storage would require scaling up the storage unit, in this case by 30 times. The impact of 5-day storage requirement on storage cost and footprint can be addressed if the energy density of these redox flow battery systems can be increased. The new solid liquid storage technology presented here allows the energy density of these systems to be increased by 4 to 8 times, depending on the active materials used. This approach allows existing redox flow battery systems to increase its energy storage capacity by 4 to 8 times with minor modifications to existing storage facilities. This means for a 4-hour redox flow battery storage system can become a 16 or 32-hour redox flow battery storage system. Or alternatively, a new 4-hour redox flow battery system with lower cost and smaller footprint. The smaller volume and footprint aspect may make this redox flow battery system attractive to the portable and transportable applications. To scale up to a longer duration, such as 5 days, would require increasing the storage volume, but with the additional volume would be much less with this high energy density storage approach. The solid liquid storage concept increases the amount of active ions that can be stored in a given storage volume while still maintain the flow battery concept. High energy density is achieved by storing the active materials in a saturated solution mixture of soluble ions and additional amount of these ions in the undissolved solid form. The ratio of the solid phase to the soluble liquid phase determines the effective energy storage density. For example, the commercialized all vanadium redox flow battery system stores the vanadium sulfate ions at 1.5 molar, or about 40 amp-hour per liter. In its solid hydrated form, vanadium sulfate has an equivalent concentration of 8.25 molar, or 221 amp-hour per liter. A 2-to-1 solid liquid mixture has a capacity of 163 amp-hour per liter, or 4-fold increase. The flow battery concept, along with its advantages, is maintained by circulating only the liquid. This eliminates the issues associated with electrical shorting between cells and high pressure drop and poor fluid distribution when conductive solid and liquid slurries are circulating. The fact that the concentration of the active materials in the solution remains constant until the solid is totally consumed yields higher current and voltage output for a longer time is an additional benefit of this approach. During operation, as the reactant is consumed and the product is generated, with a solution of excess reactant, like in this case, the concentration of the product will definitely exceed its solubility in the electrolyte, and solid precipitation in the battery can occur. So to prevent solid precipitation in the battery, especially in the electrodes and the flow channels, we developed the temperature swing method. This method is applicable to active materials with positive temperature-dependent solubility. The key features of this temperature swing method are as follows. The battery operates at a higher temperature, TH, and the active materials are stored in the tanks at a lower temperature, TL. During operation, the lower solubility saturated solution at temperature, TL, is heated by the heat exchanger on the way to the battery to temperature TH, at which the solubility of the active material is higher. At the higher temperature TH, the solution becomes undersaturated and can allow more active material to be generated in the battery. The effluent leaving the battery is cooled to temperature TL in a storage tank, where it becomes oversaturated and precipitates. As an example, the solubility of vanadium sulfate at 20 degrees Celsius and 45 degrees Celsius is 1.8 molar and 2.7 molar respectively. This 0.9 molar difference is available per pass through the battery for additional generation during charge and discharge. To illustrate the solid and liquid storage concept and the temperature swing method, the vanadium 4+ electrolyte at the positive electrode of the all vanadium redox flow battery is used. Let's start with a vanadium 4+ solid and liquid solution undergoing charging. The saturated vanadium 4+ liquid is pumped to a heat exchanger, where it's heated to temperature TH, and then to the battery. In the battery, vanadium 4+ is consumed and vanadium 5+ is generated. And the effluent solution leaving the battery is cooled to temperature TL and returned to the storage tank. As vanadium 4+ is consumed and its concentration drops below a saturation level in the tank, solid vanadium 4+ will dissolve to keep the concentration of vanadium 4+ constant. This continues to occur until solid vanadium 4+ is completely consumed. Meanwhile, vanadium 5+ concentration in the system increases. When its concentration exceeds its solubility at temperature TL in the tank, solid vanadium 5+ precipitates. Steps 2 to 5 continue until charging is completed. This process is reversed during discharging. For this process to be successful in this application, there are some operational requirements. The most important requirement is that the rate of precipitation and dissolution processes must be high enough to reduce or increase the concentration of the active ions in the storage tank at temperature TL to allow the full concentration difference to be exploited. To promote faster precipitation and dissolution, the use of nucleation materials was explored. The table on this slide shows some of the nucleation materials used: the vanadium 4+ solution concentration, and the oversaturation level to promote precipitation, and the observed precipitation time with and without nucleation materials under no stirring condition. First, it was found that natural precipitation without nucleation materials takes a very long time. It's as long as 10 days when the oversaturation level is low, and the precipitate is highly crystalline and very stable, and consequently has very low dissolution rates. When activated carbon or the H+ form zeolite Y28O2 are used as nucleation surfaces, they generate gel-like precipitates with low crystallinity and have high precipitation and dissolution rates that are fast enough for this redox flow battery application. Furthermore, we found where the low crystallinity precipitates triggered by the use of active carbon or zeolite as the nucleation materials were used as the nucleation material itself, the precipitation rate is highly accelerated. This may be attributed to the shorter nucleation time. The data given in this table are for non-stirred solution and with only 10% solid. With stirring, these rates were found to be higher. And in a high solid to liquid ratio solution, where the nucleation surface is much higher, the precipitation rate is expected to be much greater. Finally, we found also that since a certain oversaturation threshold is needed to initiate precipitation, higher active ion concentration can be created in the battery during operation, which allows for a larger concentration difference window per pass to the battery and therefore higher current density operation. That is, the concentration window will be between some oversaturated concentration and the undersaturated feed concentration. To understand the precipitation and dissolution processes and mechanisms, we looked at the known structures of vanadium 4+ sulfate in the crystal database and did some DFT calculations to determine the potential structures of the dissolved, dissociated, and undissociated ionic clusters for this vanadium salt. We can start with the commercially available material that is shown as solid 1 in the slide. This is a highly crystalline material consisting of undissociated vanadium 4+ sulfate ionic clusters. When it's dissolved in an aqueous sulfuric acid, some of it may not dissociate and form ionic clusters in which the vanadium 4+ cations are still ionically bonded to the sulfonate anions, as shown at number 2. Some of of these will dissociate into ionic clusters with the vanadium 4+ cation bonded to the water ligands and the sulfate anion now situated in the second hydration shell, shown here as number 3. This dissociated vanadium 4+ cation is the electrochemically active ion in the redox reaction. During the precipitation process, the undissociated ionic cluster number 2 can precipitate as the undissociated solid number 1. The dissociated ionic cluster number 3 can precipitate a solid number 1 through the number 2 route. Or it can precipitate as the dissociated amorphous solid number 4, where the ionic clusters are unorganized, or the dissociated crystalline solid number 5, or a combination of both. Now both have the sulfate anions still in the second hydration shell. Since the cations and the anions in precipitates number 4 and number 5 are not ionically bonded, they can be easily separated during the dissolution process, giving rise to higher dissolution rates and yielding the electrochemically active vanadium 4+ cations. The results will be shown later in this presentation. To support the mechanism study, XRD is used to look at the precipitates. This slide shows the XRD results of the as-received commercial material of vanadium 4+ sulfate solid in black. The low crystallinity gel-like precipitate in red, and this gel-like precipitate after it's stored for 1 month and 6 months in light blue and purple. The first notable observation is that the 6-month stored gel-like precipitate has the same XRD signature as the as-received highly crystalline commercial solid. This shows that the highly crystalline commercial solid is probably the most thermodynamically stable form for this salt, because with sufficient standing time, even the gel-like precipitate will eventually reorganize to form this more thermodynamically stable form. Note that even though the results are not shown here, the solid from the natural precipitation process has the same XRD spectrum as the commercial material. The XRD results show that there are basically 2 solid groups. The more crystalline powder-like group 1 solids, consisting of undissociated ionic clusters, and the lower crystallinity gel-like group 2 solids, consisting of dissociated ionic clusters. Finally, the low crystallinity of group 2 solids supports the existence of the amorphous solid phase consisting of dissociated ionic cluster number 4 shown in the previous slide. The results presented earlier show that there are 2 different solid structures for the precipitates. The highly crystalline solid hypothesized to consist of undissociated ionic clusters, and the less crystalline gel-like solids hypothesized to consist of dissociated ionic clusters, where the active vanadium 4+ cations and the sulfate anions are not directly bonded. It was also hypothesized that the gel-like solid of dissociated ionic clusters would readily dissociate to yield the electrochemically active vanadium 4+ cations. To validate this hypothesis, an electrochemical study is conducted in which the oxidation polarization curve and the open circuit voltage of 3 different solution mixtures of the same amount of vanadium 4+ sulfate in 3 molar sulfuric acid are measured. In these 3 cases, the amount of vanadium 5+ in the solution is fixed. Note that only the dissociated vanadium 4+ cation is electrochemically active. The first case is the commercial vanadium sulfate dissolved and mixed at room temperature, or 20 degrees Celsius. The second case has the same solid mixture or solution mixture as the first case, but the solution is heated for 10 minutes at 50 degrees Celsius and then cooled to room temperature before additional testing is done. Heat is used in this case to break the ionic bond between the vanadium 4+ cation and the sulfate anion. The third case has the low crystallinity gel-like vanadium sulfate mixed at room temperature. The open circuit voltage measured, or the equilibrium potential of a solution with the concentration of vanadium 5+ fixed, correlates with the concentration of the active dissociated vanadium 4+ in the solution. So if the concentration of the active vanadium 4+ cation in the solution is higher, the equilibrium potential will be lower, and vice versa. The slope of the oxidation polarization curve gives the electrochemical activity of the solution mixture and correlates with the concentration of the active vanadium 4+ cation in the solution. So the higher the concentration of the active vanadium 4+ cation is in the solution, the higher the electrochemical activity, or the slope of the polarization curve, is. The results shown on this slide show that case 3, right, the one with the gel-like material, has the lowest open circuit voltage and the highest slope for the polarization curve, followed by case 2, where the solution was heated to break the ionic bond of the ionic cluster number 2 to create the ionic cluster number 3. This study confirms that the low crystallinity gel-like precipitate in group 2 can rapidly dissolve and dissociate and contains a higher concentration of the active vanadium 4+ cation, and is the preferred solid form for this solid liquid storage approach. After we have identified the suitable precipitate form and determined that the precipitation and dissolution rates of this precipitate form are fast enough for the redox flow battery application, we want to confirm this observation by demonstrating the concept in a hydrogen vanadium flow battery system. This system is selected because it allows us to focus on only one vanadium redox reaction couple. The system consists of a 16 centimeter square flow battery and a vanadium storage tank, a heating section, and a cooling section for the temperature swing method for the vanadium side, and a flow-through hydrogen side fed by a hydrogen tank. The hydrogen is not stored in this study. The storage tank for the vanadium electrolyte consists of two compartments separated by a porous separator, with the solid stored in the bottom and the liquid collected at the top. The storage tank is maintained at 17 degrees Celsius by cooling tap water, and the flow battery and its feed are maintained at 40 degrees Celsius. As given earlier, only the liquid electrolyte is circulated through the flow battery. The demonstration was conducted as follows. First, a charge and discharge cycle was done using a liquid-only solution of 1.8 molar vanadium sulfate in 3 molar sulfuric acid at a constant current density of 100 milliamp per centimeter square, with 1.3 volts and 0.5 volt as the cutoff voltages for charge and discharge. When that's done, 33.35 grams of the low crystallinity solid was added to the solution, and another charge and discharge cycle was conducted. The results are shown in these two graphs. The solid curves are for the case without the additional solid, and the dashed curves are for that with the additional solid. First, the results show clearly that the capacity and the peak specific energy of the system are increased with the additional solid. Second, the steady state voltage plateau at the onset of charge and discharge for the case with the additional solid shows that the dissolution rate of the active solid is fast enough to maintain a constant concentration of the active ions in the electrolyte to create this voltage plateau. This plateau ends when the solid is completely consumed. As the system continues to charge or discharge and consumes the soluble ions, the system voltage changes. Finally, the shorter voltage plateau observed during discharge indicates that the solubility of vanadium 5+ in this electrolyte may be higher than vanadium 4+, yielding less vanadium 5+ solid in the system. In summary, the solid liquid storage concept and the temperature swing method allow the storage energy density of a redox flow battery to be increased significantly. The controlling factor in this approach is the rate of precipitation and dissolution of the solid phase of the active materials. The rate of precipitation and dissolution is highly influenced by the structure of the precipitates and the nucleation materials. Metastable low crystallinity structure of dissociated cation and anion clusters gives high precipitation and dissolution rates and high electrochemical activity. Demonstration of this solid liquid storage concept in a hydrogen vanadium system shows that the precipitation and dissolution rates are high enough to stabilize the concentration of the active ions in the solution when the solid phase is still present, giving rise to higher system voltage and higher energy output as an additional benefit of this high energy storage concept. For future work, first we will continue to demonstrate this concept using the hydrogen vanadium system, but with higher solid contents and more cycles. We will measure the open circuit voltage of the vanadium electrolyte to determine the dissolution and precipitation rates of the vanadium ions during operation at different current densities. We will conduct the same structure, mechanism, and electrochemical activity analysis on the vanadium 5+ material. We will then extend our study to vanadium 2+ and 3+ redox couple, and then combine all of them to demonstrate this concept in an all vanadium flow battery system. Finally, we will also apply this concept to other redox flow battery chemistries. I would like to end this presentation by recognizing the support of this work by the National Science Foundation through grant number CBET 2024375. My co-author and I greatly appreciate your attention.